All right, so let's now look at some important properties of a trig function. So we've learned that, you know, theta is being an angle. So we've learned that we can take cosine value on the unit circle of an angle theta. And that is a function. And we can also take sine function of any theta angle and come out. So this is the x coordinate on the unit circle, and this is the y value on the unit circle. And a brief reminder here is that you've got a unit circle, and okay, and at any angle theta here, then x coordinate and y coordinate on the unit circle. So that's what referring to the cosine value is here, and the sine value is the vertical coordinate. But so now once we have learned and we have seen through quite a few examples, then here we're going to look into some important properties. So briefly remind yourself that, let's say, when theta equals a zero angle in radians, for example, then what we have here is the cosine value of the angle theta correspondingly came out being value 1. And then the sine value for this particular angle theta is 0. And then we also learned that when theta, and for now still stay in the positive counterclockwise rotation, then when theta equals a pi over 6 angle, change to pi over 6 angle, then the cosine value of pi over 6 is the square root 3 over 2, and the sine value when your angle theta is changed to pi over 6 is 1/2. And then so on and so on. We've learned, so when theta changed to a pi over 4, we got positive square root 2 over 2, and then sine value for theta, we got square root 2 over 2 positive value as well. And so now let's look over to my unit circle that I have had on the screen here. So just like how we were doing on the chart right here, so looking to the unit circle, then so here is once again the angle being zero angle, and just like how I was demonstrating through the chart right here, then when your angle changed to the pi over 3 angle, then this is the sine value of the angle theta being pi over 6, and this little line right here in red ink right here, the length being a square root 3 over 2, but that these two components together is making up the x and y coordinates of your terminal point. And so obviously, just like the chart was saying, this is cosine of a pi over 6 angle. This is sine value of pi over 6 angle. And then when we change the angle to pi over 4, then notice how this animation changed the cosine and the sine value of the angle. And then further on, now we can change the angle, and let's investigate here. So as I'm making this animation, I need everybody to observe for now let's focus to the change in length, the change in the x coordinates of your terminal point on the unit circle. And so when we started out being the zero angle, let's one more time go back to that starting spot right there, but when we started out being right at the zero angle, then the length, the x coordinates or the cosine value is 1. And then as we keep making our angle change here to get larger angles, then the x coordinate actually does gets shorter, or in other words, it gets reduced to be shorter. At least here, this red length right here is not as equal length as 1 any longer. And as we keep changing to other angles within quadrant 1, it keeps getting shorter. And right now, as I'm saying, right now we are focusing on the cosine value. And then now I'm going to continue to hit my terminal point to that angle where we so-called the pi over 3 angle. And once again, the length on the x coordinate here, the length that's corresponding to the x coordinate still even gets shorter. And now let's look at some other non-common value. Let's say when you even, but the rule of thumb here is now as you keep increasing the angle, right? And before we hit to 90 degrees, before we hit to pi over 2 angle, then the length here on the x-axis keep getting shorter and shorter. And then when we hit to right here on the pi over 2 angle, then the x coordinates become 0, as you already knew it. And so let me take a pause here and go back to my board here. But so far you can see that cosine angle, when we stay, so we have changed to various different angle theta value, and we've noticed that the cosine output value so far has been either equal 1 or below 1. And so now let's get back to the demonstration on the unit circle, and let's continue further. And so now on my unit circle, I'm going to continue to make my terminal point travel counterclockwise along the unit circle. And now let's hit to that next angle being the 2 pi over 3 angle right here. And now we're going to start noticing that the length on the x-axis start getting back to being some length. However, the coordinates change to negative coordinates. So it's now the x value switch to -2. And then as the angle keeps open out further, so this is the 135 degrees, or it's the 3 pi over 4 angle, then the cosine value is a negative square root 2 over 2. And so it's getting more negative, and the length itself is getting longer, but it's more negative, meaning more negative in terms of the coordinates terms like that. And then as we keep opening up the angle, and now this is even longer but more negative coordinates. And once again, when we hit to that angle being pi or 180 degrees, then cosine is going to be, the cosine value of your angle pi is being exactly -1. So it looks like so far those angles before we hit to the angle pi has been giving a cosine value less than, a cosine value is greater than -1. Because -1 here is the furthest it hits out. And then let's investigate further. So now as I go past that angle pi equals, or that angle theta equals pi, then the cosine value gets back to become somewhere less negative compared to -1 here. So now it's the cosine value, but the animation is actually showing a little bit of a miscalculation here, but that's meant to be a negative square root 3 over 2. And then there's your negative square root 2 over 2, and then so on and so on. And so picking up from this animation, then let's go back to my board here and let's make another conclusion. So we just earlier agreed that cosine value is being less than or equals 1. And so now as we keep traveling along the unit circle, then we found out that the cosine output value can get negative. But no matter what, the negative cosine output value can only be anywhere greater than or equals to -1. And so now, as importantly as it's gets, we actually notice that this is one important property regarding the output value of any cosine function. So it doesn't matter which angle theta you're at, but the output for your cosine value, or the output for your cosine function, has to be anywhere from -1 is the least, and being at most 1, being inside of this interval from -1 to 1. And so back on the animation screen right here, to emphasize what I was saying, now let's go past that point 3 pi over 2, and the cosine value starts getting positive and more positive. and they're still getting positive. And once again, when it made its complete cycle, get back to that angle 0, or here's the angle 2 pi, then the length return to being 1. And that's our discussion about cosine value have to always be anywhere from -1 to 1. And so now what about at any angle theta? Let's find out what's important about the sine value for any angle theta. And so we have seen it through the table, and now let's once again look at my animation here on the screen. So here's my unit circle again, and currently right at the starting point, before I make any movement of my terminal point, then the sine value right now is being a 0. And then I'm going to start pushing, or I'm going to start letting my terminal point move to other angle in the positive direction. Then, and remind yourself that the sine value is now actually the vertical coordinates. And so now as I'm making my rotation here on the unit circle, then let's move to those common angles here. Then so you can see that, so now instead of being 0 coordinates, y coordinates, then my sine value now at angle pi over 6 here is now being positive 1/2. So it starts getting higher. And then now as we can keep changing, and we can change to another angle, pi over 4, then the sine value now, the vertical coordinates now, is a positive square root 2 over 2. And I hope you notice that square root 2 over 2 is actually higher than the 1/2. And the picture can show that. And now as we change to a larger angle again, to that pi over 3 angle, then the height now is still getting higher. Now it's being at sine value, or the vertical coordinates, being square root 3 over 2. And you can keep seeing that the vertical height, now the vertical coordinates now keep getting higher and higher until ultimately we hit to that angle. And let's look at some non-common angles here on the unit circle. Obviously, or apparently, the y coordinates still getting higher and higher until we hit ultimately to that angle being pi over 2. Then your output value for the sine function comes out being exactly 1. And then once we go past that point, and then getting past that pi over 2 angle, then the y coordinate still a positive coordinate, but start getting lower, but still positive, and then continue to become lower as we going further past that pi over 2 angle. So now you can see that. And so now what I recognize now is that, let's go back to my board here, but we just now recognize that it looks like at any angle theta that we're changing to, then the sine value has to be, the vertical coordinate has to be anywhere less than, lower than, or equals 1. And then let's go back to my animation unit circle right here, and then we're going to continue making that terminal point rotating in a positive direction. And now when we hit to that angle being pi right here, then our sine value gets back down to 0. And now when we go past the angle pi right here, now the coordinate starts switching over to being negative coordinate. And you can see that the animation is kind of have this coordinate hidden a little bit, but it's a negative for 1/2. So length is in terms of length, it's still a 1/2 length, but now it's as a coordinates, then the vertical coordinates became a 1/2, a negative 1/2 coordinate, and then it's become more negative, where sine value for this angle now is going to be a negative square root 2 over 2, and the angle here is the 5 pi over 4. And then as we continue to make our way to the next angle over here, the coordinate became negative square root 3 over 2. And then the angle there was at 4 pi over 3. And then so now when we ultimately hit to that angle being 3 pi over 2, then the sine value came out exactly negative 1. And then to demonstrate the idea again, so it looks like so far before we hit to that angle 3 pi over 2, then those vertical coordinates is still, well, they are negative, but they're still not as negative as being -1. And so in other words, you can see that back on my table right here, you can see that sine value can be greater than, for any angle theta, sine value can be greater than -1. And then when we come down to exactly, and back on my demonstrating unit circle here, then when we really hit down to that angle 3 pi over 2, then the sine value came down to exactly equals -1. And then when we now going past that angle 3 pi over 2, then the sine value once again still negative, but now being less negative, so indicating the fact again that sine value should always be either equals -1 or greater than -1. Now let me come and back on my animation unit circle here, then we're going to complete our demonstration by letting you see all the other sine values. And here we complete the cycle and get to that 0 value for sine. And so now what we have here again is another important property, but this is about the sine function. So it doesn't matter which angle on the unit circle you're at, sine value of theta, the angle here is theta, sine value of theta always comes out anywhere from -1 to 1. All right, and then let's look into another important property and quite famous for as a relationship between the sine and the cosine function. But now let's say you are at any terminal point on the unit circle, and then now I'm not going to be really pointing to the pi over 6 or pi over 3, but it's just these points on my unit circle here are easy to catch. And so now let's say you're at any terminal point on the unit circle, then remember that length from the origin out to your terminal point on the unit circle is being 1. And then when we actually draw the coordinates here, we form a triangular setting. And then to remind everybody, and you have seen that hopefully at this point enough, that this is now the y coordinates being the sine value of your angle theta, your central angle theta. The sine theta is here, and cosine angle theta is this short distance. But as another name, remember these are the x coordinates, and the vertical distance here is the y coordinates of your terminal point. And once again, just similar to some activity I've done earlier, if I would bring that triangular setup off from the unit circle, then, and purposely still putting that in the same exact position, then the x coordinate is here, or it's the cosine theta value, and the y coordinate is here of the sine theta value. And then the terminal point is here, where x comma y at that vertex is the x and y coordinates of your angle. The central angle of theta is right here. But in the end, the reason I took this triangle out of the unit circle is because I want everybody is to have one good focus into the picture here. But once again, what we have here is a right triangle. And so Pythagorean theorem has always been stating that. And by the way, the hypotenuse here is the radius of the unit circle, and that equals 1. So now back to what I was about to say is that according to the Pythagorean theorem, then we're looking at this length right here, the x or the cosine theta. So here directly out from the Pythagorean theorem, x squared as one of the leg here being square, plus y squared, which is the square of the other leg in my right triangle, has to equal to the square of the hypotenuse. And the hypotenuse in this case here is 1, so it's 1 square, or in short, it's x squared plus y squared equals 1. But then, right out of that, after blending in our understanding with trig function now, so x by itself can be substituted by cosine. And so what you're looking at here is cosine square of theta. That's substituting for x squared, and cosine substitute for x. So cosine square means cosine theta being square plus sine theta, sine square theta, and all that there equals 1. And so we came down to a famous, this is what we call the fundamental trig identity over here. I would usually call this the fundamental trig identity. An identity here, an identity is an equation, an equality that's regardless of which variable it's taking, but this equality always holds true, and that's what an identity is. And this identity, I have proven that immediately right out from the unit circle without substituting any value for theta into the equation. So for that reason, and anybody who has gone through the course of trigonometry will have to know this identity over here. So I call that it's the fundamental trig identity. And right after we've learned about the fundamental identity here, then it brings up a clarification that I need to address here in terms of notation. So notation. So when I was writing, and you can still see that on my screen here, or on my board here, that the notation cosine but with a square, and then it comes the input theta right there. This really means we take cosine value as far as order of operation. We take cosine value of the angle theta, and then we square that value. But in formal written form, we use this notation as cosine square of theta. But that indicates we take the cosine value of the angle and square. And so likewise, that other notation you have seen in your identity right here, and we will see this kind of form a lot of time. That so sine square, a power, basically what I'm trying to explain here is the power notation of your sine or cosine function. So sine square right here, and then it comes to the angle input. That means sine of the angle theta, and once calculated, we're gonna raise that to the square power. So that's what it means. And then, so for the rest of our journey in trigonometry, there will be many other occasions that you're gonna need to raise a, let's say, a cosine value of an angle to some high power, let's say some power n. Then we use this notation. The proper notation for this is cosine to the n. The power is indicated as a superscript right next to the trig function notation itself. And then we indicate the input variable. So similarly, sine of theta being raised to some high power n, we actually reduced all that symbol into a nice convenient symbol, sine to the n of theta.